Here is a strange failure. You hand a language model a corpus of 10,000 documents, about 1,000,000 tokens, and a question. Somewhere in that pile is the one passage that answers it. The model knows exactly which one. Its attention still ranks that gold document highest at every scale. And yet, when you ask it to name the document, it is wrong almost every time. Recall drops to nearly zero. The model knows the answer. It cannot say it. A team at Berkeley and UT Austin tracked this paradox down to a single mechanism and found 2 cheap fixes that recover almost all of the lost accuracy. The discovery is not a new architecture. It is a diagnosis of how attention quietly breaks at scale. The system is called block search. It turns retrieval into a decoding problem. You prefill a Qwen 30.6 billion model with the whole corpus in context, every document capped at 300 tokens, then append the query, and ask the model to autoregressively decode a 4-digit code. That maps back to one document. 3 design choices make this work. First, random per document codes, redrawn every training step, so the model cannot cheat by memorizing position. Second, block sparse attention, where each document attends only to itself and the query attends to everything. Third, an on-policy auxiliary loss that trains the model on its own, possibly wrong prefixes. The result matches a dense retriever at small scale, and length generalizes about 10 times past its training context. Until, near 1,000,000 tokens, it collapses. The setup is deliberately brutal. 3 retrieval benchmarks, natural questions, MS Marco, and Hotpot QA, each scaled to corpus sizes up to 10,000 documents, roughly 1,000,000 tokens. That is far beyond the 0.6 billion backbone's native context of 32,000. The model must generalize to corpora 20 to 40 times larger than anything it saw in training. The gold standard to beat is Qwen 3 dense, the same backbone trained as a classic contrastive retriever, and the Oracle reference is MSA 4 billion, a concurrent model trained 7 times larger on much longer contexts. The metric is recall at 1 over the generated 4-digit code. Everything is source first, transcribed from the paper tables. Here is the diagnosis, and it is the heart of the paper. The collapse is not a ranking failure. Probe the model at the query token and measure whether any attention head still ranks the gold document first. That signal, called R19NE, stays at 1.00 at every single scale, even at 1,000,000 tokens. The model never loses track of the gold document. What breaks is the readout. The gold document keeps the highest pre-softmax score, but thousands of irrelevant documents dominate the softmax denominator, so the gold's normalized mass collapses. The attention output is literally rewritten from a gold token average into a distractor average of comparable size. The total magnitude barely shrinks. The gold share drops from 91% down to 1%. First result, the recovery. On MS Marco at 10,000 documents, base block search recall is 0.2%, effectively dead. Qwen 3 dense sits at 20.2. MSA 4 billion, 7 times larger, only reaches 16. 2 cheap fixes recover almost everything. Score rescaling, called SS Max, multiplies the pre-softmax scores by a factor times the log of the corpus size, so the gold distractor gap grows directly with scale. And document routing keeps only the top 256 documents past layer 16. Compose the two and recall lifts from 0.2% to 20.5, edging out the dense baseline and beating a model 7 times larger. Second result, the mechanism, shown as the gold share of the layer 19 attention output. At 500 documents, the gold drives 91%. At 2,500, 18%. At 5,000, 6%. At 10,000, 1%. This is the gold to distractor swap happening inside the network, and notice the total output magnitude shrinks only about 36%. The signal is not fading, it is being drowned out. Either fix alone helps. Both together confirm the failure is a compound effect of 2 independent causes, either of which alone would not produce the collapse. The cleanest confirmation comes from a benchmark where dense retrieval fails outright. Limit demands lexical matching, something embeddings are bad at. There, the noisy baseline signal does not generalize. The gold document is drowned among near duplicates. But once score rescaling sharpens the readout, the clean signal generalizes, and block search beats the dense retriever by about 3 times across every corpus size. The model is not learning new facts. It is finally being allowed to say what it already knew. Honest scope. First, even with both fixes, a gap to the attention ceiling remains at every scale, so attention dilution is mitigated, not solved. The authors frame it as the primary open bottleneck. Second, the fixes are borrowed. Scalable softmax, attention sinks, and routing all come from prior work. The contribution is the diagnosis, not the tricks. Third, on oblique retrieval, where relevance is analogical rather than lexical, every variant stays at the floor despite a near-perfect attention ceiling. The model can rank it, it cannot decode it. And this is only a 0.6 billion model, so whether the diagnosis transfers to larger backbones is untested. The takeaway is one of the most citable results in recent memory. R19NE equals 1.00 at every corpus size, while generation recall falls to 0. The model knows the gold document at every scale, it just cannot read it out once the softmax denominator grows. 2 length-aware fixes recover the gap and beat a 7 times larger model while exceeding dense retrieval 3 times where dense fails. Subscribe for the next paper breakdown.